So a barometer is a device for measuring atmospheric pressure. And let's see how this works. Let's see what one looks like. So a barometer looks like a column, a glass tube filled with liquid. And in most cases, that liquid is mercury. We'll explain why that is in a second. So we have this tube filled with mercury, liquid metal, and the top we are going to cap off. So this is capped. This whole thing is filled with liquid mercury, and there is no air in here. You can remove all the air, so it is just mercury all the way to the top. So this is all liquid mercury. Now if we take this and put it in a container of mercury that looks like this, so this is also filled with this liquid. And I should say you can do the same thing with water or any liquid. Mercury turns out to be convenient for a reason we'll get to in a second. Okay, so if we have a system that looks like this, we can use what we've learned to figure out what's going to happen and why we can use this to measure what the pressure is of the air in the room. Okay, so here's what we see if we do this. If we try to create this, you can see that you can only make a column of mercury that goes up to some height. So the liquid ends at some height. And so there still is no air up there. At the very top, this is a vacuum. You can measure this and show that there is no air in there. P equals 0, or at least very, very, very small pressure above the surface of the mercury. Down here, we still have our mercury in this dish, and of course the mercury is still filling all the rest of our glass tube. So, what the heck is going on? Well, we know right at the surface what is touching this fluid here. Well, the air is touching this fluid, right? And air is a fluid. It is going to push down on this with its air pressure. So this, right at the surface, has the same pressure as the air in the room. So the air is pushing down on the surface and making the pressure here equal to whatever the air is in the room. Now we know for points at the same height, they have the same pressure, which means that right here in the middle of the column, this point is also at that same pressure, right? So here it's being caused by the air actually pushing on this. Here it is just because that is a fact we know about pressures, because this fluid has to be in equilibrium. We'll learn a little bit more about the fluid equilibrium later on. That means that this pressure has to be the same as this pressure. So I'll draw another little arrow pointing to that. Okay, so if this point is the same as the pressure of the air, then the other fact that we know, which is at the surface of the liquid mercury, our pressure is equal to 0. That tells us what the height of this thing is. So in other words, the height of this column of mercury, H, we know is a relationship between these two pressures, because the pressure down here is the pressure at this depth, which we know has to be the pressure at the top, which is 0. I'll just write 0, plus rho g y, the depth in the fluid at this point. So that's rho times g times h. So in other words, let's think about this a little bit more. If the mercury were a little bit higher than this, that means the pressure here would be a little bit higher than the pressure here. And overall, that would be a net force on this fluid downward that would want to push the mercury down further into the dish. If it was a little lower, that means the pressure here would be a little less than the pressure of the air, and the air would push the mercury down and force a little bit more up into there. So in other words, this is really just a condition of the equilibrium of forces, like balancing the forces on each little piece of mercury. This height has to be exactly the right height so that rho GH is equal to the pressure of the air. So as the pressure of the air changes in the room from things like weather, or if you're changing your altitude, changing your height within the atmosphere, the density of our mercury is not going to change. The gravity of Earth is not going to change. And so the height of the column, the height of this mercury level in the tube, is going to change. And so by measuring this H, you can make a direct measurement of the air pressure in the room. So for 1 atmosphere, the density of mercury is roughly 13,000 kilograms per cubic meter. I don't have that number written down, but it's something close to that. G is 9.8. You can show that the height of that column of mercury is going to be 760 millimeters. That's 0.76 millimeters. Because for centuries, this was the way to measure pressure. The units of millimeters have become stuck as a way of measuring pressure, and so those pressure units are sometimes called millimeters of mercury. So since this is 760 millimeters, 1 millimeter of mercury is roughly 1/760th of an atmosphere, which is about 133 pascals. So 1 millimeter of mercury is a pressure of about 133 pascals. All right, this unit is also called the torr, and sometimes you see torr or millitorr in pressure systems also. All right, great. So this is just kind of a fun thing that we can apply these equations to. I've said they use mercury for these, and I haven't done a great job of explaining why that is. So let me just demonstrate why you use mercury. So if we use mercury, we end up with a height of this column that's 760 millimeters, which is like, this big or something. It's 3/4 of a meter. And you've probably, maybe in another science class, you've seen a mercury barometer. We definitely have them around Science A. You can do the same thing with water. Of course, you can have the water, the pressure from the air, hold up a column of water and measure the height to the top surface of the water. The issue is the density of water is only 1/13 that of mercury, which means the height of your column has to be 13 times as big. So instead of 0.8 meters, you have something that is approximately 10 meters tall. So to make a water barometer, the physics works out okay. It's just that the thing has to be 30 feet tall. You can't fit it inside a single-story lab room. So that's why mercury is so useful, because of its super high density.